Hey there. Today we're going to be talking about block copolymer self-assembly and how we can liken it to a molecular orchestra. Without further ado, let's get into it. Act 1. The musicians arrive. So the first thing one needs to understand before we really get into depth is what a polymer is in the first place, because polymers will be our musicians. If you take one chemical unit, called a monomer, and then link it together with a couple more of itself, and then some more, and even more after that, you get a chain of repeated chemical units that we call a polymer. Now, if you have a polymer made up of more than one species of monomer, then it's a copolymer. And if that copolymer is essentially two chunks of homopolymers linked together, then it's a block copolymer, which is our focus today. You can have many types of block copolymers, including diblock copolymers, triblock copolymers, radial copolymers, and graft copolymers. For the rest of this video, though, we'll mainly be discussing AB diblock copolymers. Though, before we do, I'd like to quickly note that these other types can get really cool, and you definitely take the time to read about them if you get a chance. Okay, now seriously, just back to diblock copolymers. Some examples of the types we are interested in are polystyrene block polyacrylic acid and poly-N-isopropylacrylamide block poly-N-viryl imidazole. These polymers are special because they're what's known as amphiphiles, meaning they have both hydrophilic and hydrophobic properties. In acrylic acid, the oxygens in the carbonyl and hydroxyl groups are more electronegative than the carbons, and as a result, the electron density gets pulled towards them, creating non-trivial dipole moment, which is an imbalance in the charge across the molecule. Because the styrene group is all carbons, we don't get the same effect, and so our larger polymer has both a polar and a nonpolar segment. Now, say we have not just one, or two, or three molecules of this polymer solution, but a whole sea of them. This disordered phase is high in entropy, but also high in enthalpy, since contact between the nonpolar and polar parts of the polymers is energetically unfavorable. It's like a mishmash of sounds from all kinds of different instruments in a way that isn't the most pleasant thing to hear. Act 2. Finding their sections. Because this disordered phase is high in energy, it'll naturally seek to lower it by any means possible, in this case by minimizing the surface area between the hydrophobic and hydrophilic regions. And so our copolymers will self-assemble into a variety of different shapes, including micelles, cylinders, and vesicles, like sections of an orchestra coming together and playing as a group rather than each musician playing on their own. Just like how an orchestra's sound depends on the quality of its musicians and the count in each instrument section, self-assembly is influenced by a number of parameters, like LC, the length of the hydrophobic section, A0, the area of the hydrophilic section, and V, a measure of hydrophobicity. What structures take form also depends on the degree of polymerization, the fraction of A blocks in the copolymer, or B blocks, whichever way you want to look at it, the temperature, and the total concentration of polymer in solution. By varying these parameters, we can get all sorts of spatially periodic structures. Act 3. The conductor arrives. When these block copolymer solutions do self-assemble, they don't always do so in the neatest way. Varying rates of self-assembly, or mechanical difficulties, can cause certain parts in the solution to get frozen in their current structure. And even under good conditions, self-assembly doesn't happen everywhere all at once equally, and so we only get small grains of alignment, distributed. Even a group of talented musicians can fail to achieve the same order present when being conducted. Having this alignment be only locally anisotropic is oftentimes not ideal, and so we need a way to transform the system to become macroscopically anisotropic, which is where external fields come into play. First off, let's think about a simple dipole put under an external electric field. When it's applied, the dipole will naturally align itself with the field's orientation. Because of the block copolymer structure and the highly symmetrical shapes of self-assembly, we can do the same thing and apply an external field to a system of self-assembled polymers, like a conductor bringing clear direction and intent to an orchestra. In a bulk solution, this rearrangement happens through three main mechanisms: selective disordering, nucleation and growth, and field-induced rotations of grains. Selective disordering occurs for weak domain segregation, close to the order to disorder transition region, or when the system is mostly ill-aligned. Domain regions that are not properly aligned essentially melt back into the disordered phase before reforming in an aligned pattern. Nucleation and growth occurs for intermediate domain segregation, or when dielectric interfaces are primarily normal to the applied field. When the field is applied, a periodic ripple distortion is induced within the system, which grows with field strength exponentially. This distortion breaks down the structure into small regions that are then free to align with the field and grow from there. Field-induced rotation of grains occurs for strong domain segregation, or when the orientation is already close to that of the field. Unaligned grains are slowly rotated until they are fully aligned with the applied field. Here we have some figures depicting two of these mechanisms. In Figure A, we see alignment with the field over time through reorientation of grains at room temperature. In Figure B, alignment over time occurs through nucleation and growth, this time at a temperature of 80 degrees Celsius. We can also perform this external electric field-induced alignment on a thin film of copolymer, where improving the orientation of block copolymers forming a nanostructure with shear can prove difficult. For all the cases of induced alignment we've looked at before, the block copolymer systems have been in anisotropic morphologies, like cylinders and lamellae, which can reorient themselves to avoid an electrostatic penalty from the external field. Isotropic morphologies, however, like micelles and gyroid networks, cannot do so. Instead, when placed under an external electric field, they may transition into another order structure, as can be seen with spheres transitioning to cylinders. Similarly, at different moments in a song, a conductor may soften the string section while really bringing out and emphasizing the woodwinds. Another transition can occur, however, where instead of transitioning into a different ordered phase, these morphologies instead melt back into the disordered phase in an order to disorder transition. So, just like how a conductor controls the tempo, phrasing, and sound of an orchestra performing a piece, we can use external electric fields to induce specific orientations and structures within self-assembling block copolymer systems. And now we are ready for Act 4, the performance. The two main applications of block copolymer self-assembly I'd like to talk about today are for nanoimprint lithography and drug delivery. When high-resolution patterning is needed at very low scales, self-assembling block copolymers can be used as templates and scaffolds for later structures. First, a die block copolymer is spun onto a substrate, which is then heated and mechanically imprinted, hence the imprint part, to induce self-assembly, with the target morphologies of cylinders and lemma in specific regions on the substrate. To ensure proper spacing and a defect-free system, self-assembly is often aided by chemical or topographical pre-patterns, chemo and graphoepitaxy. Self-assembly can also be guided, though, as we discussed, with an external electric field. Now, let's take a look again at another common morphology that can be formed by block copolymers, liposomes. We can adjust and tune the structural parameters of these vesicles with a high degree of control. For starters, we can vary their size and wall thickness. Other things we can control are their surface topology and how deformed they are. But most interestingly, at least to me that is, we can add all sorts of decorations. Vesicles with polyethylene oxide, PEO, as the outer hydrophilic layer are biocompatible and don't interact with the immune system. Moreover, we can dress them with antibodies on the outside, as well as hydrophobic proteins and small molecules within the wall, and hydrophilic compounds inside the inner cavity. One real-life example of these functionalized vesicles is in the delivery of anti-cancer drugs Taxol and doxorubicin. Liposomes assembled from PB block PEO and PLA block PEO copolymers have been loaded with hydrophobic doxorubicin inside the walls and hydrophilic Taxol further within. These vesicles enter cells, and when the PLA degrades, doxorubicin and Taxol are released. In tumor therapy studies with animals, treatment of solid tumors in mice with these vesicles resulted in double the tumor cell deaths in comparison with plain injection. So there you have it, block copolymer self-assembly. It's this beautifully intricate phenomenon that, when you think about it, really does share a lot with music. Different parts that don't quite fit together, finding a way to organize into something purposeful, something functional. And similar to how music has the power to move us, these molecular orchestras have real power too, revolutionizing nanolithography, transforming drug delivery, saving lives. Structure leads to properties, properties lead to function, whether you're talking about a symphony or a nanoscale micelle. Here are all the papers and sources referenced and utilized in this video. For those interested in exploring the science behind all this in more detail, I suggest you take a deeper look. And if you get the chance, I highly recommend taking a listen to Alexander Scriabin's Prometheus, the Poem of Fire. You heard a few short clips of it in this video, but it really complements the topic and is definitely worth the full 20-minute listen. With that, thank you for watching.